Okay, so we're going to be talking today about vectors and velocity and what they have to do to each other. But before we really get into that, it's important that we define a couple important terms. First important term is something called a scalar. Okay? A scalar, just like the name sounds, it is something that can be measured on a scale, not like, a weight scale, but just like on a scale of 1 to 10, or maybe on a scale for measuring weight, or possibly on like a Richter scale. Okay? It's something that only has magnitude. So speed, I could measure on a scale. What do we typically use to measure speed? Miles per hour, absolutely right. Meters per second. What about distance? What are some different units we can use to measure distance?
Tape measure.
Tape measure is not really a unit. Okay, yards, inches, meters, centimeters, miles. Okay, fathoms, knots. No, actually, knots would be speed again. And so to kind of counterbalance that, a vector is basically the same thing as a scalar, except we give it direction. So 55 miles per hour is the speed. If I said 55 miles per hour south, then that would be the vector equivalent of speed, which would be velocity. Okay? Which, after you understand this, it makes one of the jokes from your childhood make a lot more sense. Does anybody remember the name of the bad guy in Despicable Me? Vector. Remember what he said about himself? Has both direction and magnitude. Okay? No, pretty clever. And so some examples of vectors would be like velocity, which is like speed with direction. Displacement, that's like distance in a given direction. And then forces are also vectors. And we're going to be coming back to that one quite a bit throughout the year. Okay? Because when a force gets applied, it is applied in a certain direction. You can't have a force without a direction that it's being applied to. Okay? So all of that is just kind of pregame. We're going to spend today talking about vectors. We're going to spend today sort of playing with vectors. So, slightly better definition of what a vector is right here. You can also refer to a vector as a directed line segment. Okay, if a line goes on infinitely in both directions, a line segment is just part of that line. And it's got a terminus, okay, an origin point, and then it's got a direction in which it's going, which would be the pointy part of the arrow. The longer the line segment, the greater that vector's magnitude. So we got a few different vectors right here. We measure direction on vectors relative to some kind of standard. In most cases, we're going to be measuring them relative to the positive x-axis. So for instance, if I could get an angle measurement on this, then that particular angle is going to be the direction of this vector, and then the length of that line segment is going to refer to that vector's magnitude. Okay? So we could say that this first one has, I don't know, would that be something like 20, 30 degrees, okay, north of x? And the magnitude would be, if we were to say, call it 3 somethings, okay? Or whereas this next one is going to have a, you can either call it a negative angle or an angle of decline from that point, or you could get hardcore with it and say that the angle of that vector is actually the measure of this entire thing, which is going to be 270 plus whatever that is, 90, 90, 90, and then that part of the angle there. And then you see how this vector is decidedly smaller than the last one, so this might have a magnitude of only like 1 or 1.5 or something. Okay? Different parts of the vector, you've got the initial point, which we sometimes also call the tail. Starting point, terminal point, that's the head, that's the pointy part. That's the direction that the vector is being applied, whether it's velocity, whether it is force, or whatever. Bless you. Bless you. Now the cool thing, and this kind of ties in with what we've been already looking at this year, you can refer to any vector if you think about it as being on an xy coordinate plane. You can kind of look at it in terms of its x component and its y component. In other words, you can take any vector and you can turn it into a right triangle. Which then means, what can you do with it?
Figure out its distance.
You can figure out all kinds of stuff about it. Okay? Not necessarily distance, because it doesn't necessarily have to do with distance. That's just a scalar. But you can figure out, using your trig functions, any other part of this triangle. So if you know the angle, if you know the x component, then you can find everything else that's there. Or if you know how high something goes, and you know the angle to it, then you can figure out how far away it is, or you can figure out what the total distance is from where you are to where that object is. You know how whenever you have like a point on a graph, like if this was 0, then we would call this point right here would be like 1, 1, right? You got your x component, y component. You can refer to an entire vector using pointy brackets, where you're going to make this part right here the x component, and the yellow part right here the y component. So in other words, if I was to represent this vector, not necessarily telling you where it starts, but if I was to represent the direction and magnitude of it, what I could do is I could look at the x displacement. So starting from this point, going to this point over here, how far over is it? Okay, that's positive 9. So this is going that way. And then the y component is going to be from here up to here, so 6. And again, pointy brackets. So that's another way of notating that vector. Okay, did I go too fast? Does that make sense? Okay. So, I'd like you to take just a minute on your own paper. I would like you to make pointy bracket notations for vector A and for vector B. You told me a second ago you had no questions. I'm calling on it. Let's see if you can do it. Jot it down on your notebook somewhere. Helpful to remember, like it says down here. You've got an x, y axis right here. That's positive x, positive y, and negative y. Bless you. So I'll call your name. Either you've got it or I'll help you figure it out. Okay. Avis, what do you have for the notation for vector A?
9, -2.
She's got 9, -2. Okay. Anybody get anything different than that? 8. Okay. Well, let's do a count here. Okay, starting from there, we go 1, 2, 3, 4, 5, 6, 7. Yeah, it is 8. Okay, and that's fine. That's fine. Easy mistake to make. So are y'all okay with 8, -2? Okay. Why -2?
Because it's going down.
Because you're going down. Exactly. Okay. Very good. Abby, what'd you get for B? 4, 3. Did anybody get anything substantially different from those? Okay. Let's check. Yeah, 8, -2, and 4, 3. Very good. All right, questions on that? Still good? Okay. So if you've got 2 points on a vector, and again, we refer to those 2 points if I've got a vector like this one here. Then we've got the terminal point, and we've got the initial point, right? If I have 2 points along there, or let's say that I know what the coordinates are for my terminal point, my x and y, and I know my points for my initial point, x and y, then I can use something very, very similar to the, what is it called? y2 minus y1 over x2 minus x1? Slope form? Okay. All right, point slope form. Thank you. All right. So if I've got my terminal point here, this up here would be x sub t and y sub t. This right here would be x sub I and y sub I. Very sub there. Oh, fancy. Yeah. Okay, flawless. So then you're going to do your terminal minus your initial. In other words, you're going to do x sub t minus x sub I is going to be your x component. Y sub t minus y sub I is going to be your y component. Okay. Here we're not doing the y over the x. All we're doing is we're just finding what the resultant would be for each of those two, for the x pieces and for the y pieces. Anybody has any questions? I hear a lot of whisperings. See some people still squinting and scribbling, so ignore them. Okay. So find me the pointy brackets form of a vector that starts at point -4, 3 and ends at point 8, -7. So take just a minute and do that. Which of those would be your initial point? Which ones are going to be your I?
4, 3.
Okay, so that's your I. So this right here would be where it ends, it terminates, so that's going to be x sub t and y sub t. Be careful when you are subtracting negative numbers. Sophia, what'd you get? 12 over negative 10. Say again? 12 over negative 10. 12 over negative 10? Like that? Okay. Anybody get anything substantially different, or do you all agree? Okay. See a few people looking around, looking confused and or angry. Yes? Okay. Well, let's see here. If we're going 8 minus negative 4, right? Then that becomes 12. Okay. And negative 7 minus 3, they're both the same, so they get bigger. That equals negative 10. So yeah, absolutely right. Supposed to do terminal minus initial. Yeah, good rule of thumb, if you're looking for change, you do final minus what you started with. Okay? All right. So now we're going to do something called vector addition. And this is going to be all kinds of fun. There's two ways that you can take several vectors. Let's say that we've got a dog. No. We've got a steak, right? Big, fat, juicy steak with, like, the T-bone in it. That totally steak, right? Okay, there's a steak. Now, we've got 3 doggos who are pulling on said steak, okay? We've got small doggo who we're going to use this little green vector for. He's pulling it that direction. Medium doggo is trying to pull it that direction. Very large doggo is pulling it that direction. So if I want to know where the steak is going to end up moving, what I have to do is I have to take all of these vectors in their different directions and their different magnitudes, and I've got to add them together. And what I get from that is something called a resultant. Okay? And it's super fun, super cool, super easy to do. Okay? Basically, all I'm going to do is I'm going to link them from terminal point to initial point. Okay? So what I'll do is I'll take this doggo, I'll take the next doggo, and put that right there. Third doggo is going to take that right there. And my resultant is actually going to be, and I didn't mean for it to be like this, from this point where the green one started to this point where the black one ends. So the steak is actually going to end up moving with a resultant that big and in that direction. Which means that big doggo with the black vector is going to win the steak, but it's going to be a very, very slow pull. Okay, because it's such a short vector. So something kind of like this. So if I've got vector W and 2 vector V's, if I want to find out what the resulting vector is, then I take that W, I stick a couple V's on it, tail to head, and then my final resulting vector or resultant starts here and ends here. Okay? Okay? Seems simple, right? So here's what I'd like to do. We're going to take this formula right here, which is 2v plus 3u, and I'm going to get 2 voluntoles to step up to the board, and they're going to build this for us, and then they're going to draw in the resultant with the black marker. Okay? So my 2 voluntoles. No, she's already been voluntold today. So is she. Maybe I'll have sticky sticks. It's going to be Chase Keener and his lovely assistant, Samantha. Y'all come on down. All right. So build for me 2v plus 3u. I would recommend maybe starting over here somewhere. What you're going to do is just grab this and bring it down here and then build off of that. Okay. Now what's my resultant going to be? Start at the very first starting point. Uh-huh. Yep. Put an arrowhead. Okay. That's my resultant vector. Very nicely done. Y'all give him a hand. Great hand. Okay. Now, let me ask you a question. Does it matter what order I put these arrows in order to get this resultant? Yes or no?
Yes.
Liz is shaking her head no. Chase is saying yes, it totally does. Okay. Let's find out. So if I take these arrows and kind of scramble them up a little bit here, let's start with U, and then U, and then U, and U, and U, and hey, take a look. It's not exactly perfect, but same resultant vector. So when you're adding vectors together, it's just like adding any other numbers. It doesn't matter what order you put them in, so long as you have initiation point going to terminal point on each one. Let's do this one. Gonna get a couple of voluntold. This time it's gonna be Random and his lovely assistant, Jacob. Come on down. All right. Now, before you start building here, what's something that you see in that equation that kind of gives you pause?
-4.
There's a negative. So how am I going to have a negative vector? What do you guys think?
Tilt it downward.
Okay. Tilt it downwards. I like it. So if this entire thing is from this point to this point, what would the negative of that vector look like? Would it be just pointed up? Be up and back the other way. So let's take this, let's flip it, and let's flip it again. Okay. So there is the -4. Now, or the -u. Now, how many of those do you need? Okay, let's just clone them a few times. Whoa, my dude, where'd you go? What have I done? I killed it. There it is. Clone. Saves. What happened? Okay. There you go. Go play. I'd recommend maybe starting over here somewhere. And put them in any order you want to.
So it's only one W.
Oh, you can still grab one W whenever you're ready for it. Okay, bold move.
To put it here, you just kind of do that. That's
Okay, so I think I gave you one too many, but that's fine.
One, two, a little bit down here. Like that.
Okay. So draw me a result. Do it in black. Do it. Okay, that's their resultant. Scramble it up and see if you get the same thing going the other way. What if I start like this? And they've got it. Does it take me to the same place? Pretty darn close. Okay, I think these might have been spaced a little bit different. Okay. Questions? All right. Okay. Cool. All right. So now what I want you to do is I want you to write me the vector equation that gives me this resultant right here. Okay, do this on your binder. For example, by vector equation, here we had negative 4u plus w. Here we had 2v plus 3u. So what's that going to be? Jot your answer down. Reed King. Yeah. So what do you don't have to come up, but what do you think the vector equation is for this?
R equals 2v plus 3u plus w.
Okay, did anybody get anything substantially different from that? What'd you get?
We did minus 2v, so that's 3v.
Why did you subtract it? But they're not. They're going in the same direction that they were before. The u's are going in this direction. The w is going in this direction. Okay. Yeah, all we're doing is we're adding. We had 2 of those, 3 of those, and 1 of those. And yeah, totally 2v plus 3u plus w. And again, it probably doesn't make any difference what order you put those in. You're still going to get that same result because what's that property of addition? Not distributive, communicative property? Does that sound right? Yeah. Cool. I think that's the thing. Okay? Doesn't matter what order you put them in if all you're doing is adding them together. Okay, so now we're going to have somebody geometrically represent this equation, and then they're going to come up with the resultant vector. And so we've still got a few names in here. I think we're going to get a couple volunteers. Haley Jones and her lovely assistant, Celeste. Come on down.
I need one of these. It won't go.
Here's your knuckle. Oh, you wait. No.
I broke it in there.
You broke it. Hold on. Control Z. All right.
You can try.
Use your knuckle.
I'm not.
Use the knuckle.
Haley.
Here, she got it. She got it.
It's the fun part of life.
It is the fun part of life. All right.
Okay,
You want to get a W?
a dummy?
And then we can add our little V's?
I can't.
Push hard. It's not a phone.
Yeah, you just gotta add some force in there, Haley.
There you go. Okay.
I'm building.
Minecraft?
No.
There you go.
I didn't know this is the way we would continue.
It makes a cute little trapezoid. That's not a trapezoid.
We need another one.
You do?
Yeah.
That says
Oh my
3D.
god.
Okay.
Yeah, it makes it a little.
All right. So draw me a resultant. Wait. Before you do, let me scooch these just a little bit. It'll make the math work ever so nice, slightly nicer. Okay, great.
I can't draw a straight line.
Okay.
That's okay.
Starting point. That point.
I told you.
It's kind of almost a straight line, maybe. Let's see.
Looks like a snake.
The resultant snake. Oh, a thing of beauty is a joy forever. Here, go ahead and put a head on it. Put a head on that snake.
Until it gets ugly.
All right. So there's the resultant vector. Now don't go anywhere. Wait, actually, you two can go somewhere because Nick is going to come up here, and he's going to give us the form of that vector right there. X part, Y part. Step on down. You got this, Nick. Do the X first. What's the difference in X from left to right?
10.
Okay, we'll write a 10 down and the X spot in the brackets. How about your Y? From bottom to top. Just from this point up to the line where this point is.
Oh, 1.
I think so. Okay, so he's got 10, 1. All right. What do y'all think? Agree?
Yeah.
Okay, gravy. Now, let me ask you a question. Could we get that even if we weren't able to like directly draw that? Could we get that just by getting all of the X's and all the Y's from all of these? Okay. So for the green, check it out. Each green has an X of 1 and a Y of 2, right? So this is 1, 2. This is 1, 2. What's the red's X? 1, 2, 3, 4, 5. Okay, what's its Y? Negative 2. Okay. How about the blue? What's its X? 2. What's its Y? Negative 3. What if we add up all of the X's here? 1 plus 1 plus 1, that's 3. Plus 5, that's 8. Plus 2, it's 10. Okay, 2, 4, 6. Minus 2 is 4. Minus 3. There you go. Same way. Same thing. Okay. You can also combine them algebraically, which is kind of what we just did right there. This is geometrically. We're actually drawing a picture and connecting dots. Okay. But that second part of what we did right there, we're combining them algebraically, meaning we're taking all of the X pieces and we're taking all the Y pieces. Or what they've got right here is 3 of these vectors equals this resultant vector right here. We could do that right here. We could do 3 of these 1, 2's. 3 times 1 is what? 3. 3 times 2? Okay. And so just this piece right here is 3, 6. Agree?
Yes.
Okay, easy peasy. So you combine the X components, then combine the Y components. So what if I take this plus that? Okay.
12 minus 6.
12 negative 6 plus 5, 4.
5, 4.
So what would that be?
17 negative 2.
17 negative 2? Nailed it. It is. Yeah, very nice. Questions? All right. Okay, so we're going to, okay, no, hold on. Have we already done this one? U plus 3B plus W? Okay. So let's algebraically do this one instead of geometrically. On your own paper, I would like for you to give me U plus 3B plus W. What you're going to probably want to do is you're probably going to want, is that the one we just did?
Yes.
Well, spoilers then. I guess that's going to be 10-1 again, huh?
Maybe.
Yeah, looks like it. Well, it stinks.
I think that's
We're out of slideshow?
darn it.
Nope. Unacceptable. Unacceptable. So we're going to come up with a new thing.
I accept it.
I can't accept that. I can't just go home. So here's what we're going to do. We're going to do 2W plus 2V minus 3U. Okay? I would like you to do 2W, 2V. I'm sorry, wait. That should be plus. Not bad. 2W plus 2V minus 3U. Okay? First thing you need to do is you need to be sure you know the values of all three of those vectors. It's a multi-part fun times thing. I really hope the sound has been picking up well on this recording and or my computer hasn't died. You know, we got some real bangers in here. And what we're going to do, just so there's no pressure here, is I'll pull a popsicle stick and that person can tell me what answer they got. If someone got something different, we'll write that answer down too. If somebody got something else different, we'll write that answer down as well. And then we'll see how many people got each of those and see who got it right and who's still not quite there. Oh, that's all kind of messy. Random, I am curious as to your final answer. Do it. Okay, I'm hearing hearing some Avis is giving a Avis, what did you get?
I got 2 answers.
You got one. You got
Okay.
one.
Okay.
-9, 4.
-9, 4. Somebody get anything different than those? Let's tally them up here. Okay, so we're going to add all of our x components. So I've got -15, 14, 13, 12, 11, 10, 9. So I'm getting -9 for my x. And then for my y's, I'm getting 2, 4, 6, 8, 10, 7, 4. So yeah. That's it. What I had to do, remember, if we're going minus something, we have to basically take the negative of this, so that becomes -5, that becomes +2. Okay? So, that's your introduction to vector addition. Tomorrow we are changing gears yet again, and we're going to be talking about various kinds of motion graphs, which ties back to the lab that you did last week and finished up yesterday. Yesterday? It was a short week. So we will talk about it when I see you again.
It's like I got a puppy.